So I spoke at the ARM Research Summit last year about SpiNNaker. I guess not everybody here was there then, but this year I'm giving an update and a slightly different perspective. The research questions that underpin SpiNNaker are the issues of what we know about how the human brain works, and can we use the kind of computing resources that are becoming available today to accelerate our understanding of the brain. And as we learn more about the brain, can we use that knowledge to build more efficient computers, where more efficient might mean more energy efficient, more parallel, higher performance, more fault tolerant, and so on. So those are the two headline research questions that underpin the work I'm talking about. Now, while we've been doing SpiNNaker, which has been going on for quite a long time, it's been 20 years in conception and 10 in construction, and most of you will know that certainly over the last decade, there's been remarkable progress in a different direction in computing that is to some extent inspired by the brain. And these are the deep networks and the convolutional networks that now dominate the world of machine learning applications, and they are the kind of neural networks that come into play whenever you talk to Siri or Alexa on your phone or in your home, and whenever you do searches and image classification and so on. And these neural networks really represent a re-emergence of second-generation neural networks from the 1980s. And Jeff Hinton revisited his 1980s idea in about 2004-05, and had some new insights and discovered that computers were a lot faster, and found that what was impractical in the 1980s had become practical, and basically that's caused these huge changes in machine learning over the last decade or so. These networks, I'm going to say, are quite unlike biological networks, even though they're inspired by biological systems. They're based primarily on dense kernels. They use abstract neurons that produce continuous outputs, whereas biological neurons spike. They don't produce continuous outputs. They're predominantly using feed-forward connections, although some more recent developments have introduced a little bit of feedback. And they're trained through this gradient descent technique called error back propagation. They're very effective, and they've had a huge impact. But they're not very like biology. So if you look at what we do know about biology, and of course, one of the problems of talking about the brain is that we still don't fundamentally understand the operational principles of the brain. We know quite a lot about the details. So if you look at the brain, here's a simplification of the path from the retina in the eye through to the cortex. And what you see is that almost everywhere where there's a connection feeding forward, there's a similar connection feeding back. So if A connects to B, then B connects back to A. And that's almost universal, apart from at the sensory periphery. So we've got fundamentally different operation from the start. In fact, if we now go and look inside one of those cortical layers, which are labeled V1, V2 here, we find even internally the connectivity is far more complex than the greatly simplified networks that are used in machine learning systems. We see that the neurons in the brain predominantly spike, so they don't produce continuous outputs, they just go ping occasionally. And while you're sitting there, one of the things you can muse on is the fact that all your thoughts are just complex patterns of pings between neurons in your head. Eventually, if you think about this enough, you go mad, I'm sure. But so I don't recommend it. There's a kind of two-dimensionality about the brain, but another difference from the machine learning networks is the connectivity is sparse. So in machine learning, the connectivity is generally dense, and that means you can compute those networks using dense matrix operations. In the brain, the connectivity is universally sparse. And so if you going to represent it by matrices. They're sparse matrices. Now, currently, if you want to compute with ConvNets, then you find that the hot favorite is the GPU, and NVIDIA is making a very strong play in this space. GPUs are good for ConvNets because, of course, they're very good at dense matrix operations. Whether they'll be able to support more biological networks is questionable. These systems use quite a lot of power, and the ARM community, I know, is interested in seeing if this kind of functionality can be moved out towards the edge of the system, which means bringing the power consumption down dramatically. One of the techniques that's moving a bit in that direction has been the observation that we don't need to compute these networks in double precision floating point. In fact, already the trend is towards much lower precision, even down to 8-bit ints as the fundamental unit of computation. So there are moves in that direction. You might think if we model biological networks, things will get better, but currently the state of the art in modeling cortical systems is to go to supercomputers, where we've gone from kilowatts to megawatts of consumption. That's going the wrong way. But now we can support the kind of sparse matrix operations that are required, and we can use the spike-based communication we see in biology. There is an alternative to going to the supercomputer, and that's this technology which has the label neuromorphic, brain-inspired computing. And here there's been a trend, again, as I say, this has been quite a separate thread from the deep learning and convolutional net trend, because it's been primarily driven by building brain-inspired systems, so with the objective of looking at the biology and understanding the biology rather than building applications. But here, the trend is to move the memory much more locally to the computation as a way of getting the power down, and these systems can potentially run in real time, which is actually not possible on the supercomputer. Even with your megawatts of compute, the communication on a supercomputer can't support real-time spiking operation. But now we can go from megawatts down to milliwatts by reconfiguring and reorganizing the computation in a more brain-inspired way. So that's generated a lot of interest in neuromorphics, and this interest is manifest, for example, in the 2014 MIT Technology Review, which listed its 10 breakthrough technologies as it saw it. And here in it, halfway down the list, the neuromorphic chips, where the description says microprocessors configured more like brains than traditional chips could soon make computers far more astute about what's going on around them. That's a very interesting promise. I've no idea how to deliver on it. But it's showing interest. And the following year, the World Economic Forum announced its top 10 emerging technologies in 2015. And if you look here, in at number 9 is neuromorphic technology. In fact, if you look at this list, it's quite interesting because at least 4 out of the 10 are in the sort of AI machine learning space where neuromorphics could have some impact. So next generation robotics, emergent AI, sense and avoid drones, and the neuromorphic technology itself. So half of the top emerging technologies approximately are in this space. The most recent statement on this was the report to the President of the United States ensuring long-term US leadership in semiconductors, and this was published in January this year. Now, this report is interesting in many respects, one of which is it was written for a president who at least had a chance of understanding it. The world has changed since then. It also displays an impressive degree of paranoia about progress in China in semiconductors. It's quite interesting to see the American view of Chinese progress. But anyway, in this report, they propose technologies that could ensure long-term US leadership in semiconductors, and you'll see there at the top of the table is neuromorphic computing. And time frame available now. Of course, this is very much influenced by IBM's presence in this game. And the description here, which you may or may not be able to read, talks about continued R&D into new architectures coupled with 3D technologies and new materials, deep learning accelerators for mobile and data center applications, and applications for true brain-inspired computing. So it's actually covering the sort of deep learning accelerators as being within the neuromorphic technologies, but it talks about this as something that's available now to have a major impact. And of course, the most visible contributor in this space is the IBM technology. IBM TrueNorth is the biggest chip that IBM has ever made. It's 5.4 billion transistors, 1 million configurable neurons, and this is scalable in the sense that they can put multiple chips together, and the board here has 16 of these chips on. And IBM has started demonstrating some interesting applications. Of course, to build a chip with this density involves compromise, and one of the compromises is that the synapses connecting these neurons are essentially binary, which means that the ability to implement learning on the chip itself is very limited, and IBM basically does the learning in software systems and then downloads trained networks onto the silicon. Just down the road from IBM, who developed this technology in Almaden in San Jose, is Stanford, and there Quebe Nebohan has been leading this project called Neurogrid, and he's now working on a descendant of this about which little detail is currently available. But unlike the IBM system, which is entirely digital, it's asynchronous digital technology, the Stanford Neurogrid uses sub-threshold analog circuits to model neurons and delivers similar energy efficiency on a much older process technology. And here there's 1 million neurons on a circuit board. Still in the analog domain, our partners at Heidelberg in the Human Brain Project are building above threshold analog neural circuits. Because they're above threshold, they operate much faster. One of the challenges with analog systems is to slow them down to biological speeds, and Heidelberg doesn't do this. They run at 10,000 times faster than the biology that they're modeling. They've built some very interesting technology. They're doing this at wafer scale, and they have recently demonstrated that they can embed an 8-inch silicon wafer in a printed circuit board. So they have a multi-layer PCB where one of the layers inside the board is an 8-inch wafer. Good fun. And our own contribution here is the SpiNNaker project, which is what I'm primarily here to talk about, and our goal from the outset has been to think about what we could do if we put 1 million mobile phone processors, that means ARM chips, into one computer. And the basic sums tell you even with 1 million ARM processors, you only get to about 1% of the scale of the human brain, or as I prefer to think of it, 10-hole mice. The mouse brain, conveniently, is about 1,000 times smaller than the human brain, but in many biological ways, very similar. So modeling the mouse brain is a good intermediate target. And we've been building this for a long time. I described the architecture last year, but basically it looks like a conventional, massively parallel system with a mesh interconnect. Each node in the mesh has 2 chips in it, the compute layer, the SpiNNaker layer that we designed at Manchester, and a conventional industry standard memory chip. So these are put together in a single package with some basic 2.5D packaging. And then we can tile the world with the attractive logo black plastic package shown at the bottom of this picture. The chip itself, again, I covered this last year, but It's basically a bunch of processors. There are 18 ARM 968 processors on the chip. Remember, we started designing this more than 10 years ago. And each of these processors has its memory very local to it, and this is the key to getting reasonable energy efficiency. But all that's fairly standard. It looks like any other massively parallel computer, except it's very simple. The key to the machine is how we connect them together. As I've said, the communication on supercomputers isn't suitable, so we've built our own system, and that's embedded in the packet switch router in the heart of the chip. And SpiNNaker's basic routing is multicast because neurons in the brain are very highly connected. So whenever a spike is emitted, it may need to connect to 10,000 other neurons. And we implement the multicast through an associative routing system. We built a range of machines from the board with 4 chips on, which is about the scale of a pond snail brain, up to a 19-inch rack, which will get 100,000 cores, and that's about the scale of a mouse brain. And then the Human Brain Project platform, which anybody can use. If you join the HBP community, you can submit jobs to this machine. And that has 500,000 ARM cores, and we're still expanding it towards the original target of 1 million. That big machine is not the only one around. We've been shipping systems to groups all around the world, and there are now well over 90 systems in use on pretty much every continent apart from South America. I don't know what the South Americans are doing wrong. And in my own group, we've used the machine to solve some interesting problems. So Gabriel, is Gabriel in the room? Yes, he's sitting near the back there if you want to know how he does this. He's the man to talk to. He's developed a system that solves constraint problems. So these are problems which in principle require a non-deterministic Turing machine to solve, but he's shown that you can solve them with stochastic neural networks based on some work by Wolfgang Maass at Graz. And this system solves the very hardest class of Sudoku problems. The hardest example is the one shown on the right. The one shown on the left is relatively easy, and there's an intermediate one in the middle. And you can see from, well, I don't have time to explain the graphs, but basically the hard one takes longer to solve, but it's still only taking seconds to produce a solution to a very complex constraint problem. Another constraint problem is coloring maps, and again, the same basic neural network system will compute map coloring, and the third example that Gabriel has demonstrated is solving Ising spin systems, which again are sort of NP-hard compute problems, and neural networks with the order of 100,000 neurons and tens of millions of synapses will resolve these problems using stochastic techniques. Those are some practical applications. On the biology side, we've worked with modelers at Jülich in Germany who have a very detailed biological model of the cortex, and we've been able to run simulations of this model which incorporates 77,000 neurons, 285 million synapses and so on, uses 2,900 ARM cores on SpiNNaker, and we can compare the results that we get with SpiNNaker, which uses fixed point arithmetic, compare that with the double precision float result they get on their supercomputer, and we can show that the two systems essentially produce equivalent results. We are developing new hardware, and we're at the sort of intermediate definition stages of SpiNNaker 2 with our collaborators in the Technical University of Dresden in the Human Brain Project. And here we're planning to integrate 128 to 160 ARM Cortex M4F processors onto a die using GlobalFoundries 22 nanometer FDSOI process. And this will deliver, because we're using the single precision float version, this will deliver something around 30 gigaflops for a 1 watt chip. So just to conclude, we've been thinking about this for 20 years and making it for more than 10. There's quite a lot of hardware out there now, and the big platform is freely available through the Human Brain Project. Industrial AI has taken a different trajectory, but there's a growing expectation that Neuromorphics is going to cross over into that industrial AI path and will contribute particularly to energy efficiency and particularly to enabling these very large networks to be moved out towards the edge. SpiNNaker may not be the ideal delivery platform for those applications, but it's a very good research platform because it's very flexible. Everything in SpiNNaker, apart from the interconnect, is software. So the neural models are software, and the synapses are software. So you can use it to model any of these systems, and SpiNNaker 2, which is coming in a couple of years, will be about 10 times better in terms of performance and energy efficiency. And I will stop there. So.